Thank you, Andrew. Thanks everybody for coming. Today's presentation is about the new unscented Kalman filters and its application to launch vehicle navigation using GPS. So we'll start with the motivation of this work. So for launch vehicle, conventionally it uses radar to navigate, to find the positions. But in recent days, you have seen that SpaceX is launching some launch vehicle which can do some complex maneuvers. So for these complex maneuvers, we need onboard capability in the launch vehicle. And for onboard navigation capability, GNSS is the most preeminent method for low Earth orbits. So GPS provides us, GPS or GNSS, this provides us pseudo-range measurements, which are range with added some noises and some errors. So from these ranging equation to get ranging measurements, if we want to get the position information, we need some estimation algorithm. And extended Kalman filter is widely used estimation algorithm for estimating the states for dynamic systems, because it's very efficient, it's robust, and the performance is very fast. So computation is very fast. So, but the problem with EKF is that if the non-linearity is higher, its performance degrades. And then there's another filter called Unscented Kalman Filter, which is well-known method for nonlinear applications. It can handle high nonlinearity and give us a better accuracy than extended Kalman filter. But there's a problem with Unscented Kalman filter, which is it is computationally very expensive. It takes a long time to process. So it's hard to implement it in real time on board. So we'll start a brief discussion about description of Unscented Kalman filter. So start with a generic estimation problem. So for estimation problem, we have to express the system as state vectors, and this state vector's time evolution is described using a nonlinear stochastic differential equation. So y is our state vector, and this nu is a noise process. We call it a process noise, and the differential equation is nonlinear. So this function f is nonlinear, and this is continuous time. But our measurement in discrete time, it comes in after 1 second, 2 seconds, 3 seconds, or depending on the measurement frequency. So that's why it's a discrete time measurement. And what Unscented Kalman filter does is that, say we have a posteriori state. So since it's a stochastic and dynamic system, we are interested in the mean state vector and the error covariance. So let us assume that we have a posterior mean state and error covariance. So in normal extended Kalman filter, it takes the posterior state and use this equation to propagate to the next time step using by integration. So we cannot use a continuous time integration in computer. It has to be done it has to be done numerically. So for EKF, it just takes this state and propagates to the next step, and it assumes that this is our a priori mean at the next time, but which is not right, which is a good approximation for mildly nonlinear system, but for highly nonlinear system we have to do some rigorous approximation. So there comes the Unscented Kalman filter. It uses the error covariance to create deterministic samples, and each of these states are propagated for from going from t to t plus delta t. So suppose we have n number of state elements in the state vector, then Unscented Kalman filter creates 2n plus 1 sample, and each of these samples are propagated. So this takes a substantial amount of time for calculation of mean state vector and error covariance. So what we are proposing for reducing this time, so for reducing this time, we are proposing a new filter which is called single propagation Unscented Kalman filter, where only one sigma point, so these points are called the sigma points. So only we can approximate this by propagating only one sigma point at the next step and create other 2n sigma points by Taylor series approximation. So we can use a first order Taylor series approximation. So say these intervals here, this is our a priori mean, and these are the samples. So this interval is del yi, so for particular ith sample. So we can use a first order Taylor series approximation here after propagation to map the all the states at time t plus delta t. So if we use a first order approximation, then in calculation of mean, the error is will be in the order of second order Taylor series approximation. But unscented Kalman filter can predict till second order Taylor series approximation, so this is not exactly correct. So for that we can go for another more better approximation called extrapolated approximation, and which results in the extrapolated single propagation unscented Kalman filter, ESPUKF. Here what we are doing is we are using Richardson's extrapolation. So when we use what is Richardson extrapolation? Suppose we have a method 1 which which approximates with delta yi, and we have method 2 which approximates with delta y by 2. Then if we use 2n2 minus n1 as approximation, then all the error will be on third order. So we are actually using this approximation, we are eliminating the second order, incorporating the second order terms in the approximation, and all the error will be on the third order and third, fourth and higher order, which are for most systems which are not really important. So that's how the new filters work, and that's how it reduces the processing time as only one integration is required. So now the application to the launch vehicle. So for launch vehicle, the dynamics of launch vehicle is very complex, and so what we are interested in position. So traditionally, the position of launch vehicle is expressed in a downrange distance, this, and the altitude, local altitude. So that will give us the sense of position of the launch vehicle, and we always assume that most of the time what happens is that this trajectory is planar trajectory. So to express this time evolution of x and h, we need to know also know the velocity, the drag, atmospheric drag, and also the thrust, and also the flight path angle, which is the angle between the local horizon and the direction of the motion of the launch vehicle. So how nonlinear it is, to give you a bit of sense. So this is a simulated trajectory or simulated velocity profile of a launch vehicle. So what is happening here is that when we start the first stage, so this is our paper rocket. So in the first stage we turn the engine on, and it accelerates and velocity increases. At this point, what happens is that the fuel in the first stage depletes, and the first stage is separated from there. So due to this separation, there's a jerk. So because suddenly previously we had a continuous acceleration, and then suddenly we have no acceleration, and then stage is detached. So there will be a jerk, and then the second stage kicks in. So then it starts again accelerating, and here we can see that this region is nonlinear. This is also very nonlinear due to this jerk. So how do we simulate? So because we can't have a launch vehicle and test it, so we have to simulate everything. So what we did was that we built a model of the launch vehicle in MATLAB and propagated it in by integration, and that we considered as reference trajectory. And then we use this reference trajectory in SPIRENT GNSS simulator. So this is the SPIRENT GNSS simulator. We use the reference trajectory, and the SimGen is the software interface for the SPIRENT. So we put this reference trajectory in SimGen and command to simulate. And what SPIRENT does is that it provides us the GNSS measurement as if that the receiver is on the launch vehicle, and it gives us the GPS satellite position. So those information goes to the estimation algorithms, and we compare with the reference trajectory what is the output. So we tested for extended Kalman filter, unscented Kalman filter, and the new filters, SPUKF and ESPUKF. So this is the result. So you can see that the error for extended Kalman filter is here. So, and unscented Kalman filter is here. And SPUKF reduces the error a bit. ESPUKF almost matches the extended Kalman filter, unscented Kalman filter. So definitely the new filters have better performance than the extended Kalman filter, and the ESPUKF is almost similar with the unscented Kalman filter. So now about the processing time, because our main pitch is the processing time, how much it reduces. So for extended, here we plotted the processing time in x-axis and average position error in y-axis. So extended Kalman filter error is high, is very fast, but unscented Kalman filter error is very small, but its processing time is very high. So SPUKF position is here, so it reduces the average position error. Also processing time is much less than the unscented Kalman filter. For ESPUKF, the error is much again less than SPUKF, and also the processing time is less than UKF. So that means this filter is the most optimal solution for our application. So there is another interesting observation. So what we did was that we used 4 GPS supplies, 6 GPS supplies, 8 and 10. Obviously when the number of observation increases, our error will decrease. So that reflects here. So for 4 satellite, the error is here. For 6, error is here and decreases, and 8 and 10 also consecutively decreases. Interesting observation is that if we use traditional least square for estimating position, then what happens that error divided by or error standard deviation divided by dilution of precision multiplied by the sigma of noise. So that should be constant for all cases, but what we can see is that it varies for Kalman filter. It varies for Kalman filter. This is an interesting observation, and we'll talk about this later. So now, what we did was that we did a Monte Carlo simulation. That was what I showed. The previous result is a time varying for one case. So we ran this 200 times for 4, 6, and 8 and 10 observations. So you can see that. So extended Kalman filter average error in every time is really high for 4 satellites, and SPUKF has in between, and ESPUKF and UKF are almost similar performance. So this is for 4, this is for 6. For 6 you can see that error, EKF error has been decreased, but not as much as the UKF families. And for 8 and 10 also, error has been decreased again, but performance is always the unscented Kalman has a better performances. And the processing time is plotted here. So after that, what we did was that we incorporated UNSW Kia GPS receiver, which is optimized for launch vehicle application. So that we used here. So what we did was that, so SPIRENT, now instead of taking directly the pseudo-range just from SPIRENT, the SPIRENT is now providing the signal to the Kia receiver, and it is calculating the pseudo-range, and we are using the pseudo-range from the Kia receiver for estimation. So for using Kia observations, what we found was that for extended Kalman filter is very bad accuracy, and unscented Kalman filters give us better accuracies. But interesting thing is that here the unscented Kalman filter performance is bad than the new SPUKF and ESPUKF. So which I think is because of less noise. So UKF tends to work better within higher noise level. So in less noise, the smoothing effect of UKF decreases. That's speculation. It's not well proven yet. And now the conclusion. So we have developed 2 new filters, SPUKF and ESPUKF, and performance of these filters are better than the EKF, and ESPUKF performance is matched with UKF. And for the processing time, average processing time reduction of SPUKF is 83% than the UKF, and for ESPUKF it's 69.14%. So we have done a bit further research after this experimentation. So previously, last year in ION, we presented the satellite navigation using the SPUKF. So there we found that the UKF and SPUKF has a similar performance, but the dynamics of satellite is also nonlinear. But again, we have found that for launch vehicle, UKF are better. So we wanted to know that what is the difference between the nonlinearity of launch vehicle dynamics and satellite dynamics. So now we have a conclusive answer to this question. So we can quantify the nonlinearity, and this is called the nonlinearity index, and the performance of unscented Kalman filter respect to the extended Kalman filter is related directly with the nonlinearity index of the system and measurement. So higher the nonlinearity, better the unscented Kalman filter performance. That was previously just a speculation, but we have proved it theoretically now. And then I have showed that there's an interesting observation that the error ratio, that error divided by PDOP multiplied by sigma r, which varies for Kalman filters, but for least square it should not vary. So for Kalman filter there is a hyperbolic relationship between the standard deviation of the Kalman filter and the DOP. So that's why this variation happens, and furthermore, these application to these new filters are not really limited to space. So because this is a generalized filter designing, not particularly for space, we just applied to launch vehicle and satellite and re-entry vehicle. But it can be, these filters can be used to any nonlinear systems, highly nonlinear systems, and we expect it will perform much better. Thank you very much.